same with spec meltdown. So theory, people know about this for a long time until they actually demonstrated a work on majority of the chips out there. Suddenly, the chip makers paid attention. So the theory, this existed a long time. If people know there's a caching difference, people know that speculative execution and so on will cause issues until the paper actually showed practically they can actually steal secret. People weren't paying attention. So yes.
How do you fix this without taking out everyone's chips?
So depending on that, okay, obviously Intel is trying to fix it, right? So you can turn off speculative execution, take a performance hit. That's one. The other one is you want to separate your data so that in browser, JavaScript used to have this gigantic array that's shared on one page. Different script can share this array. Now they decided in JavaScript we can't have that array anymore. So that's one way to force a isolation. This probe array cannot be shared by people anymore. So there are different approaches to do this. And you can also rewrite your program to be more secure, right? That's a lot of the constant type crypto, a lot of the work in the side channel attack is trying to do. Then you have to battle the compiler, because whatever you put in, the compiler decides is useless. It doesn't understand security. It's bad for performance. So you have to make sure the compiler doesn't do bad things. Yeah. You can flash, do auto flashing here and there. Yeah. Yeah, experts can.
Yeah, so
people more.
I love the cryptography stuff that goes anymore. Like if you have something that implements AES, it's not actually being run in software. There's a hardware support for that, so nothing is actually touching the cache for you to look at it. It's usually that's often approaches to just let the hardware do it.
Also depends on the system, right? If your system is highly sensitive, yes. Otherwise, people don't bother. Like, what are the chances there is such a motive attacker to take that, right? All right, so the last example, a little more tricky. It might have to be some JavaScript code. So the setup here is that I want to contrast information flow from access control a little bit. So this is the best example I can find. This is actually real-world attack published some security paper. So in our browser, you'll have the plugin, right? Doesn't matter which browser you use. For example, Zoom has a little plugin. Your ad block has a little plugin, right? Your password manager has a little plugin. So these, they're not called plugin. In browser, they're called extensions. In Chrome, they're called extensions. In Firefox, they change the name often. At one point, it's called add-ons. So they're basically little programs written in JavaScript. Browser have a special way of integrating them so that they got access to fancy features of browser to improve your browser performance. Now these plugins can do very bad things because most plugins have the power to actually look through your web request before browser gets it. So they can rewrite your request, inject content, so on and so forth. So in response, so Firefox decided that, we need to ask permissions for these little add-ons or extensions. So for example, if you want to access file system, you have to ask for a file system permission. If you want to execute, you have to ask for special execution permission. So this is quite common now that you download app on your phone. Before you install the app, doesn't matter which OS you have, not Android or Mac OS, doesn't matter. It will tell you this app would want to access your contacts, your location, yada yada. Do you want to grant it or not? Right? So this is similar architecture here. So let's assume that I actually have two apps. These are good add-ons. These are written by professionals. They serve a purpose. So there's nothing malicious about these two add-ons. So one add-on is called FlashGot. It's a mass download application. So for example, you want to download a whole bunch of pictures or small bits of movies you want to download at the same time, you stitch together whatever you want. So this app essentially have a global variable called file. The programmer would specify the list of files to be stored, where to download from. This is a good application. Presumably, the user installed it so that they can download stuff, right? So they give permission to this good app. Then there's another app called Grease Monkey. Doesn't matter what it does, but one specific feature we care about is that it can actually start the editor based on a variable exe. This is the path where your editor is stored. You might have VI, you might have Emacs, or whatever editor you have, right? Again, this is a app written by a well-known person. People download this for good reason. Therefore, they granted the permission they actually want. Now, in the browser in the Firefox, the older infrastructure, not the current infrastructure, the older infrastructure, these apps actually share the same environment. They also share global variables. If I have a file named global, other people's add-on will see the same global variable as me. Right? This, from PL perspective, this sounds bad. Scoping, no scoping there. But in the web world, it's a Wild West, still Wild West. Right? So now this attacker is very smart. It basically found these two apps. I mean, this is not the only two pairs. There might be multiple pairs in the app space that can do this. Together, they can accomplish something. So the attacker is going to leverage this tool, download malware, then execute it, have the user execute it somehow unknowingly. So I have two pieces of code. Let's see. The left actually should be set up first. Yeah, sorry, this is JavaScript code. Yeah, so let's see the right side first. So this is basically, because once these apps are installed, anybody can call their API, right? It doesn't have to be a programmer clicking through to do stuff. Another app can also call the API provided by these two apps. So these two boxes are attackers' code. Attackers add-on require no permission because it doesn't directly access anything. They just want to use existing apps, right? So existing add-ons. So the first one you can imagine is going to set up a place for the mass downloader to download the malware, right? So it's going to say that basically there's a URL where the attacker have put the malware here, and then where it's going to store, it's going to put the path to be a specific location, and then here, so that's how they use the download, right? Specify malware and say where it's stored. You can imagine where they want to store, right? They want to store to the global variable where the editor will be started by Grease Monkey, right? So when you have these two pieces of code, now the Grease Monkey thought that it's actually loading an editor, except this path was modified by the attacker. It's actually pointing to the malware being downloaded by the mass downloader, right? So here, combine two apps with permissions. This attacker's app, the Firefox browser, does not ask for any permission, manage to download malware and execute. Right? How do you think about this for a while? How do you solve this problem? So it seems like access control-wise, there's nothing too wrong going on, because these are good apps. Yeah.
Seems really bad that they share the same global scope.
That's one problem. Yes. In the web, there are lots of these instances. Yeah. JavaScript itself is also a bad language to begin. Exactly. So that's the point, right? So it's weird that the attacker's app tried to call app with permission somehow weren't asked the permission, right? This is weird. This is actually one key difference between information flow and access control, in that a lot of times access control is very local. It just see the immediate step to say, do you have permission for this or not? The moment these people say, I'm going to make this a public API, the permission system won't ask other people to use this public API, right? So in some sense, sometimes people call these apps confused deputy, right? So because they act on behalf of the attacker without permission to do dangerous things, they themselves didn't ask for permission, right? So from information flow security perspective, you should transitively make sure whoever is using this should have the right quote-unquote permission for it. Right? So this is like a classical problem with somewhat local-ish enforcement mechanism of access control. Any question about this? But we'll go back to this example once we introduced information flow security a little bit. See how we actually solve this problem. All right, so okay. This is the example where this is not a secrecy problem, right? I didn't leak any secret. What's the problem? What property is being violated? Integrity, right? So intuitively you are thinking that if I want to execute something where this variable pointing to the path that I'm going to execute should be hopefully written by someone highly trusted, not by the attacker, right? If the attacker somehow can manage to change my data in an unauthorized way or cause me to perform action I shouldn't be performing, that's typically indicating an integrity issue. All right. I got this. Any questions before we move on? All right. So okay. So you have bad examples, right? So the goal of information flow security is trying to prevent data from leaking to attackers, also prevent attackers from influencing the system. Right? All the examples are counterexamples of an information flow secure system. So all the examples I showed you actually violate information flow security. Right? Okay, so now I'm going to go into history a little bit. I start by access control. So this multi-level security was actually introduced under the umbrella of access control. And eventually people figure out this is actually more information flow than access control. Right? So this is actually a very practical problem. So in government, you have various documents that contain various different types of secret of various different levels, right? So we have a government employee salary. This is actually considered in US, not everywhere else. In US, this is considered public data. Right? We should know how much the government employee is getting paid. Right? This is taxpayer money in some sense. And then the military contract, it sounds like general public shouldn't know, right? Because who do they purchase from, how much they pay for, what are they purchasing, seem to be quite important. Right? And then we have something called nuclear law code. Right? This is actually highly secretive. Only a few people hopefully know this code. Right? So these documents actually contain different levels of secrecy, if you think about it. Right? Now how do I make sure the right people get access to the right set of files? Right? In the concept of access control, I want to make sure unauthorized user cannot access these kind of secret documents. Right? So I'm going to have two people. I've not been able to access for obvious reasons. Let's say we have President and we have Homer Simpson, right? So in your mind, probably the President should have access to all these files. Homer Simpson probably only should have access to the government salary. So how do I manage the system? So multi-level security is actually saying that I'm going to have multiple security levels. So here I give 4 levels. We have public, confidential, secret, top secret. So every level is, we call higher than the other, meaning is more secretive than the other. Fewer people are allowed to read file with those labels. Right? So in terms of how do I manage the system, how to enforce this property, is that I'm going to give, I'm going to give all the files a security label. Right? So let's make nuclear launch code top secret, the military confidential, and then the government employee document public. Right? Now I'm going to give people clearances. Right? So who has any clearance for anything? If you enter NSA, you'll be asked to take a test and then get clearance. So nobody here have clearance. Let's say the president have clearance level for top secret. Homers like us have no clearance, meaning that we just give a public clearance, which means they only read public data. Right? So once I label this, I need to figure out how do I match the request of coming from a person with the file they're requesting to read or write. Right? That's where this Bell-LaPadula model comes in. The citation is on the bottom. This is from MITRE, published in the early 70s. So they have 2 policies regarding read and write. The first one, they call it simple security property. To me, I call it policy, but doesn't matter. It's called no read up. So the idea is that if you look at the label, if I go up, the more secret data is being labeled. So if you have a lower label, you're not supposed to read anything that's higher than your clearance, right? So that's the intuitive read policy here. So for example, I'll give you this nuclear file example. When the president wants to read, well, I'll compare the clearance with the file. If it's equal or higher, we're fine. So here's equal. So this read is actually okay. Now Homer wants to read it. I compare the clearance with the label of the file. Homer's label is not equal or higher than top secret because it don't have public. So the first one is allowed. The second one is denied. Right? So that's a read policy here. Right? So this is essentially preventing secret leakage because if I allow such a read, I'm leaking secret to people who's not allowed to read it. Yeah.
What about writing up, or is that just looking secret?
Yeah, we'll do write up later. Yes, you already see the problem of the LP model. Okay, so that's all good. In terms of writing, so writing is saying no write down, right? So let's follow the same secrecy leak here. Again, I'm not going to use X. I can't do it. So let's say that we have a public internet channel that people want to write to. both President and Homer try to write to it. When I'm doing writing, I'm comparing label. The channel you want to write to has to be equal or higher than your label. Because if you're writing to a more secure channel, that means you're restricting the audience, which is okay. But if you're widening the audience, typically that's a problem, right? Homer is fine, right? Homer doesn't know anything. Whatever Homer wants to write on the internet web about anything, that's totally fine. There's no secrecy leak whatsoever. However, if you're a president that tweets something, this shouldn't be allowed, right? So that's why the picture, yes, the picture has been Obama or Biden. I'm not being able to. Because the student will say, hey, but the president actually tweeted stuff. But that's actually signal same thing. It doesn't matter which one. This will write down policy. So any question about this? This is intuitive, right? If you write to a wider audience, you are leaking information, right? Writing to a wider audience means you're writing down the label. All right, so one of you already figured out this is a little bit weird because let me change the file a little bit, just get our label back. So as a result of our write policy, it seems like Homer can write to anything. Because from secrecy perspective, that's okay, because Homer doesn't have any secret. Write to anything, it seems fine. But intuitively, this is really bad, right? It doesn't seem right. I don't want Homer Simpson to write into the military contract, buying the wrong thing. He might buy too much donuts rather than buying the thing I want, right? Things like this. So what's the problem here? Why BLP this ballot model doesn't quite work? Something intuitively seems wrong. What's the problem here?
There's a piece of integrity.
Yeah, so BLP is about secrecy, right? So what we're worried about is integrity, right? This is someone we don't trust. Now they're writing the message with our file is supposed to come from trusted sources. This is really bad, right? So therefore, the follow-up paper 2 years later, they introduced a model called BIVA model. This is actually trying to use the same multi-level security to deal with integrity, right? So now we're going to change label around because it's not about confidentiality anymore. The files still have intrinsic label about secrecy, but now let's switch our focus on integrity. So for integrity, we're going to change the word saying who's trusted, who's less trusted. So notice I already flipped this a little bit in the sense that I put untrusted label on top, and then on the bottom I have mostly trusted label. So if you think about the attacker, right? So Homer can be viewed as attacker, where this person essentially has this untrusted label. All right. So basically here I'm going to label the files with what the information in the file, what the trust level of this information in this file, who can write to this file essentially. So here I give nuclear launch code most trusted, contract very trusted, and government employee salary trusted. That's some labels I randomly assign. So now BIVA have policy that essentially again compare what's high, what's low. I already flipped this. Let's see if this after I flip this still makes sense. Let's see. So I'm going to put this nuclear launch code cursor on top. So this file contains not only highly sensitive data, but also should come from highly trusted source, right? So when we compare label, this trusted label, it seems like the president should be able to write it, but Homer shouldn't be able to write it, right? This is the paradigm we want, right? So basically, if we look at this, if I flip the letters, like we did before, this is actually the same as BLP, saying that you shouldn't write down, right? Because I put highly trusted on the bottom, I put untrusted on top. So this write down, again, that actually works, right? However, because I flip letters, so sometimes people call BIVA BLP upside down, right? Some people don't flip letters. Instead, they change what they say about whether you can write up or down or not. But it doesn't matter. The point you want to remember is that when you write untrusted source, shouldn't write to trusted source. But the other way is okay. If I want to read, I can. If my API requires trusted data, it's okay for me to take data from super trusted source, more trusted than me, or same level, but I shouldn't take any data from untrusted source that's lower than me. Right? Okay, so this kind of fixes that problem, right? So that means that when I look at a piece of data or people, there are kind of sort of two separate properties, secrecy and integrity. I can assign different labels depending on I care about secrecy or integrity or both. Right? When I care about both, I should probably do a combination of these labels to make sure things happen the way we want. Right? Any question about this? So here, we talk about attacker, right? So here, essentially, depending on the label, attacker, so here the attacker, because we're talking about access control, right? The potential attacker are anybody who could have access to the system, right? Now, depending on label, so here we intuitively think that Homer have untrusted public label being the attacker, right? Because this person does not have, shouldn't have access to secret, also shouldn't mess with highly sensitive files. The files should come from highly trusted sources. Okay, so this was still in the access control realm. And then comes the seminal paper, this lattice model by Denning. This is like a year after. So they're still doing it under access control, but here is really, you kind of see the components of information flow security. So now what we're good at doing is build models, right? We're going to summarize systems like multi-level security, what they're trying to do. So we have a formal model made of a tuple of 5 fields. So in the future, we're going to shrink this down to fewer. So because we're thinking about access control, so we have objects like data, file, whatever we want to read. Then we have principals, sometimes people call subject, that want to read. It can be a person, can be a process, and so on. And now we have security classes, like the secret, confidential, whatever label we have for secrecy. This security class can also be the integrity label that we care about. And then we have this arrow, it is our intuitive understanding of what's high, what's low, where data can flow. And then because you're going to combine data, right? So therefore we have a join operator. So they wrote OPLSS in this paper. If you combine a piece of data from public employee salary, you have another piece of data from military contract. If you put them together, what label should be on this combined file? So this join operation is telling us how to actually do this, right? So essentially, this join needs to take the least upper bound, right? If I take a confidential data and public data, the combined file should be confidential, right? Because I need to protect up to the most secret data in this file. Right? So that's Denning's paper. So in Denning's paper, given this lattice label, we can model both BIBA and BLP in the exact same way, right? We just have to instantiate our classes, so security classes differently. BLP, we have secrecy labels. It's throughout the field, just to be simpler. For BIBA, I have trusted and untrusted labels. It's sort of flow-to relation. When we have 4 labels, essentially you can flow from low to high, but you cannot do any direction that's not allowed by this arrow. In BIBA and trusted model, you can go from trusted to untrusted, but not the other way around. Right? And then this is a join operation. If I put 2 pieces of data, one is open, one is secret, the resulting label should be secret. For BIBA, if I take a piece of data trusted, another piece is untrusted, the resulting should be untrusted. Right? If I flip the lattice upside down, these operations actually are quite in line with each other. All right, so how do I combine these two into lattice model? Now, even given the example I have both a secrecy angle and a target level. How do we go about this? What would be the instantiation of me doing BIBA plus BLP? Any thoughts? It should be actually quite simple, yeah.
Seems like your labels are probably like a cross product.
Yes. Yeah, exactly. Yeah, it's a cross product, and you leave the join with the individual joins, right? And then the arrow has to both flow, and you have this arrow. Yeah.
And it seems like files are secret open, and then people are just interested, or are people going to be secret open just interested?
So here, people can be, so program data are the same thing at the end of the day, especially if you have, parallel function or whatever. So yes, everybody gets the same label. Doesn't matter whether people or file. So data and process get the same label. They both have the trusted, also they both have the secrecy and integrity aspect of things, right? So are you allowed to run the secret? How trusted are you to modify this data? These two are independent aspects of it.
If they were like sort of the same, why are they two different sets of models? Or
people,
why
yeah.
are they different?
Oh, this is an old access control model where you have object and subject.
Oh,
Yeah, so now in programming language world, we have program data, they're the same thing. Programs are data programs, yeah. And so we're going to change this slightly to actually get into more of the modern information flow stuff. Right. All right, so any question about this? If you want to do homework, you can do this product. It should be very simple. Just draw the letters you want. All right, so basically in this model we addressed a few things. The target system we have is kind of access control system, right? We can generalize to in general software systems. That's okay. So iteratively we kind of look at this and say, hey, here are anybody in the system could be added depending on what clearance they end up getting. Security guarantees. This one is a slightly question mark. We'll come back to this point. So intuitively, in our mind, you're thinking, oh, attacker is not reading the secret file. The attacker cannot mess with my file, right? But we're not mathematically specifying what is my security guarantee yet. Approaches, because we're in access control world, we kind of sort of are using runtime monitoring. We're saying, hey, when the requests come in, I'm going to check the labels, make a decision to deny or not. So that's the typical runtime monitoring approach, right? When the system runs, I will make decision, right? That's the approach that so far this multi-level security system are taking. Right? Okay, so let's just get to the more modern security lattice. So it's very similar to what Daniel proposed, except we get rid of the P and N. Instead, the most important thing, typically we have a pair. One is a set of labels. I should use a fancier L, but PowerPoint is a bit tricky to use fancier L. So I have a set of labels, right? This label can be the set of secrecy you have, or the integrity, or the product of secret integrity, or other labels you want to design. That's fine. Then we have this in Denning's work. They have this arrow. So now we have partial order. What's less than the other? In terms of secrecy, if I say A is less than B, it meant A is less secretive. It can be viewed by more people than B. Right? The integrity is that A is more trusted than B. Right? So now, typically in this model, an attacker is associated with a label. Right? They were given a clearance in the old terminology. So the attacker can interact with the system bounded by this label is given. Right? So typically, given this label, the secret in your system have a label. Actually, for integrity, it's the same thing. The data you want to protect have a label that's not lower than this attacker's label. Any data or program labeled by L that's lower or equal to attacker's label is considered attacker can see, also considered controlled by the attacker. So that's the modern security lattice we're going to work with in terms of programs. Okay, this is not too far away from the Deming model, right? We just get rid of the object, subject. We're not in this access control then anymore. We want to be more generic, and we want to specifically say what's an attacker. So here is our definition of attacker. We also clearly define what are the data we want to protect. Right? All right, any question about this? Okay. So now we said, well, we're kind of having about the security property. So the property we care about is called non-interference. So it should get introduced in the 80s. It's kind of interesting to read a paper back then. I think they're still typed by typewriter, so it's very badly scanned. It's worth going to actually download these old, like 80s paper. Kind of interesting to see. So when VMAN and VLP use the word property, in my mind, they're policies. They're fairly what we call local policy. Like in true access control fashion, what we say is when this access is happening, what's allowed, what's not allowed. Right? So intuitively, we can kind of sort of say that, oh, the user with lower label cannot read higher files, or files with higher labels, secret cannot be written to lower files. VBA is similar, right? Low integrity user cannot write to high integrity files. Low integrity file cannot be read by user that require high integrity data in some sense, right? That's kind of slightly local. So non-interference is this well, you'll see the jargon here people use still to this day. It's considered an end-to-end extensional property in a way that is not tied to specific BLP. So in general, we're thinking of a higher level modeling of a system, what we want to happen, right? So this 9 difference, again, in English, what we're trying to say, if we're thinking about secrecy, is that the secret in our system should not interfere with observation of the attacker, right? So the attacker are someone who's not allowed to see the secret, right? We'll formally define what interference means in a little bit, right? So this is saying, doesn't matter if you're doing BLP or some other enforcement. Here is what we have in mind is that in our system you have some secret, you have an attacker interact with the system, also observe what's happening in the system. We want to make sure that no matter what the attacker is doing, the attacker, by looking at the system run, cannot somehow learn the secret. Right? So here the word is not obvious yet, it is interfere with yet. But that's intuitive reading of 9 difference. For integrity, the same thing, except we're talking about trusted, non-trusted. So here, the attacker, think of data from the internet, you download it from somewhere. So these are untrusted data. Oh, sorry, these are users. These are, they cannot interfere with the operation of trusted users or trusted programs. Right? So their right to nuclear launch code is a trusted operation. The internet data shouldn't impact the operation what to write to nuclear launch code. Right? All right. So this is more global property, saying the end-to-end as the program runs, what I want to happen. BLP specification of no write up, no read up, no write down is more of a local specification saying what should happen on one step. So that's the main difference between the significance of this paper that define non-difference for information flow security. It turns out BLP does satisfy non-difference. It's just the way they define it is not non-difference. Okay, any question about it? Or what makes it more complete later? Yeah.
The last Viva thing I didn't understand. Integrity files can be read by high integrity users.
Yes.
Because I thought that Viva was about writing. So why can't high integrity user, like why can't Biden Twitter in Viva?
So if Biden's about to make a decision based on Twitter data, you wouldn't want that to happen. So that's why. Yeah. So for example, your system about to shut down, so you're waiting for a command to shut down or to erase all your files. You don't want that information come from the internet attacker saying, hey, wipe all the file now. So that's the integrity part. Yeah, I think the problem with using human is because humans take different input sources and act upon different things. Because Biden can also be on vacation, do whatever they want, right? So then they can do really whatever they want. So there is no separation of the roles. But in general, when you think about program, we're thinking about these dedicated programs moving to specific things. So I'm going to also generalize this program model, right? We'll get rid of this object. Subject is access control lingo. So instead, we'll have a system. This can be a program, can be your access control system, doesn't matter. But generically, we'll have a system that compute upon the inputs, produce outputs. So here, let's just assume I have just have secrecy, have 2 labels. Obviously, you can have different